Please note that the quiz is Wednesday of week 13. Now, everyone gets to a week when they have 2 different bits of assessment and then stresses out because you've got assessment all over the place. Feel free to finish the workshop this week, and then you won't have to worry about compiling workshop and quizzes and all that sort of shit in week 13. So you've got lots of time to do it. Really, there's not a huge amount of work involved. The work is finding the actual thing and doing up SolidWorks drawings of it. The analysis, for most cases, if you understand what the load cases are, should be about an hour's work. Okay? The sorts of things that you can do on a quiz or an exam is the same sort of analysis you're expected to do for this workshop. It's just that you're doing it for a real thing that you have to find. Alright, so that's what the time-consuming part is. Please don't leave it till Thursday of week 13 because you guys will have a heart attack and you'll be knocking on my door screaming at me. You've got plenty of time to manage your time wisely. Please manage your time wisely. Alright, who had a go at the problem? Did anyone finish it? No?
Sorry Dave, just on that, can we get when will we be looking at getting workshop 1s back, just so we can sort of see where we...
Nick should be finished those almost immediately. Yeah, I'll follow.
Just a little comparison so we know.
Yeah, you should be able to get it back hopefully this week. He's actually taken longer than he normally takes, but he's not on campus regularly, so that might be why. I'll write a note, follow that up. Nick, I will let you know. Yes, it would be my intention would be to get it back basically now. But, it will be very soon, if not, tomorrow, the next day. Cool. All right. Any other questions on that? Quiz 2 is on my list of things to finish this weekend. Yeah. Sorry, I've been away for a week and I'm doing other things. But yeah, that's on the list as well, guys. It's one of those semesters where everything kind of has. I think everyone's under the pump this semester, so my apologies for taking a little bit longer on that. Alright, so what I'll do is we'll go through the last couple of steps of that problem from yesterday, and then I've got a problem that's a little bit easier that you guys can have a crack at. Alright, so we basically got to the point where we knew all our forces, right? And if I were to draw, we knew all of our forces and we decided that the top right-hand bolt, and if I have that in sort of a 3D view just at the back plate, we've got a bolt here, a bolt here, and a bolt here. That one, they all had, those top 2 had big axial forces and the bottom had a little axial force, and the top one, or all of them, had an upward direct shear force. This is the force from the bolt on the plate. And then like that. Okay, so we had the axial load that we calculated, we know what those are. We had the direct shears, so these were, the bottom ones was 3,636. And then these ones were 14,545, should have. And then we calculated those 3 as all being 8,000. And then these ones from the torsion, we actually calculated what those were as well. And the top 2 were 6,100 and the bottom one was 6,800. So this one's a little bit more, but that one's lots less. And they are 90 degrees and those are less than 90 degrees, so our determination just from looking at all of the solution was at the top right bolt. Now if it's ambiguous, or if you're unsure, or if you're unconfident in your decision making around, feel free to analyse a couple of places and boil it down to 12 mices, and the biggest 12 mices is the one you analyse. Okay? Now, obviously we could kind of combine them, but if we want to do bomboisis, we need this diagonal one in X and Y components, or horizontal and vertical components to do it. Kind of the same as what we did with the weld group. Does everyone remember what we did with the weld group and we avoided needing to do our trigonometry because we used the distance from the centroid up to the top edge and the distance from the centroid over to the side? Remember that radius that we used was in the actual stress calculation, and we were able to do that because we had an I value for the actual shape of the weld. Alright? Now we don't have an I value for a bolt group because theoretically that's a cylinder and they're all separate. So we can't do that. Alright? You could do that if you wanted to, but you'd break it up into those components initially, and then when we did the sum of the moments step, you'd have to have two components in that sum of the moments for every single bolt, which is kind of as much of a fluff around as just calculating the angle and doing the I's and J's. Alright, so it's up to you what you want to do. Look into it, but it's not as easy for welds to just calculate the X and Y components straight up. We need to use trigonometry in this one. Cool? So what we need to actually do is we have that same thing. We're going to calculate this one, and we need to calculate, let's give it an axis. What am I doing? Interface like that. Let's call this X, Y, and Z. So we need to calculate this X component, we need to calculate this Y component, and we need to calculate this X component. So, force in the Z, we have a value for that of 14,545.45 newtons, which is what we calculated. The one up is going to be the addition of the 8,000 and the upward component of our torsional vector, and you guys can do your signs and causes on it. I worked that out as this, and I'm reasonably sure it's right. 8,000 plus 6180.93 is our magnitude of this diagonal, and this up one is cos 33.69. That equals 13,142.85 newtons, and F in the X is equal to negative 6180.93 sine 33.69. And I get that as 3428.56 newtons. Is everyone good with how I got those? Yeah? Vectors, etc. Now, we've got three forces. This one results in axial stress, these ones result in shear stress, but the equation to all of those are quite simple. So, tau in the X is equal to V on A, so that's this guy. It's equal to negative 3428, sorry, that's a negative there. 0.56 on AT, which is the area of the bolt. You could have just area A or whatever, but in the table for the bolt sizes it calls it AT, so that's why I'm using AT. Tau Y is V on A, which is this V, so we could call them V's if we want. And that one could be called a P, because it's equated to a full P. Whatever you want. 13,142.85 on AT, and then stress in the Z is equal to P on A, which is equal to 14,545.45 on AT. Alright, so we have components of stress that look aligned with the axes that we want. We have an equation for formices, which we're quite comfortable using now, hopefully. Formices, when we have all of those things, is the square root of the sigma one, plus 3 times tau x squared plus tau y squared, equal to, take 1 on AT out the front and put all of that other stuff in there, and I get 1 on AT 27,659.33 pascals. Cool. Same as what we did with welds. With welds we carried the T because T was the unknown. With bolts, we're carrying the A because it doesn't make sense to us to, as I said yesterday, to calculate an A based on a D and all that kind of stuff when AT is read straight off the table just as easily as the diameter is, so we might as well just carry that through and not stuff it all up. Alright, so as you did yesterday, we equate the ball mices to the proof load for static load. Static. 1 mices equals SP on N. Table 10.5 is where we get SP for our ISO. 650 megapascals, which I think I told you yesterday anyway. Therefore, 27659.3, whatever that is, 3, on AT equals 650 E6 on 6. AT equals 2.553 E to the minus 4 meters squared. If I want millimeters squared, is that going to be a bigger number or a smaller number than that? Bigger. Bigger by how much? A million? Yeah, 1,000 squared. Exactly. Good. We're getting comfortable. So that equals 255.32 millimeters squared. Good? Right, so the last thing you need to do is read that off the table and choose the bolt size that's the area is closest but larger than that. Now for the example, I'll put the bolt table up on the slide so you have it all. Hopefully something you have a textbook as well. For this one, I'll assume that you trust me. You can choose 2 bolts. In almost every circumstance, there's 2 options, a fine thread and a coarse thread. I'm happy for you to tell me one, the other, or both. Alright? It's up to you. Generally speaking, if there's not a huge difference in diameter, then a coarse thread will be fine, unless there's a really specific reason that you need to use a fine thread. They cost a little bit more, and you need to be very careful. Oftentimes, if you specify something to be tapped, you might actually need to get a special tap kit for fine threads, whereas most workshops will have coarse threads. Most good workshops will have both, obviously. Alright, so from table 10.2, we choose size, and I'll give the 2 options. M22 by 2.5 is the coarse thread option, or M20 by 1.5 is the fine thread option. Alright, both of those are about 270 something millimeters squared, and the one below that is 180, 190 thereabouts, so that's about the gap that you're sitting in. Cool. We definitely don't want custom bolts. There's almost no circumstance where you want to make a custom thread. It just becomes astronomically expensive. Alright, any questions on that? Easy enough? Right, so from where we got to where you get here, it's a very simple step. Complexity comes when we start talking about pretension, but we'll deal with that next week. Alright, everyone confident to have a go at this? I'll give you a minute just to get that last. Is anyone still copying down, or everyone's got that? I'll give you a minute to finish copying that, and then I'll put the slide up. Good. Excellent. There we go. Alright, so as that warmed up, you can start to see what we've got. SAE class 8.8 steel, so that tells us what our proof load, etc. is. Does anyone have their textbook or access to it, or do you want to write that down? As you're writing it down, let me just find the proof load for that so you don't have to look it up. Proof load looks like is 600 megapascals. So proof load is 600 megapascals for an 8.8 volt, which you'd read straight off the table. I will provide those tables to you for the exam. As far as quizzes go, you'll need to have all that stuff, but you've got textbooks. Hopefully all of you anyways. Alright, so we've got, I've done a little ISO here, so you can see we've got 2 bolts and a force down. Those bolts will obviously have axial load on them, so it's exactly the same in terms of the way that that plate is sort of bending itself off the wall. So you'll have to work out that ratio based on the stretch of them. They will have direct shear on them, but you can see because the bolt force is in the sort of the plane of the bolts there, there's going to be no rotation on the bolt, so that simplifies things significantly for you. And the 2 things you need to find, one is if the shear is carried completely by friction between the plates, what size bolts do you need? And so effectively all you're analysing is the axial load, like what the quick example you did in partway through the problem yesterday is. And then if all of the shear is carried by the bolts, then what size bolts do you need? And it's interesting to actually know the difference in bolt size between those 2 options. Alright, so get through that. Let's get as far through that today as we can. Once everyone's got this page down, I'll pull up the bolt size chart on the slide so that you've got that there to use when you need it. Sounds like most of you are starting to get the axial forces on these bolts. So which one's more, the top one or the bottom one? Top one obviously stretches further. What sort of numbers are we getting for the top one? Almost 19 kilonewtons in the bottom one. 4.7. Does that make sense to us? We've got 10 kilonewtons here. Let's look at this with engineering eyes. 10 kilonewtons on the end. We got 19 kilonewtons there. Does that make sense? And why does it make sense is the most important part. Yeah. So the height of those bolts is roughly half the actual length there. So you can imagine that the extra lever arm certainly you're going to end up with more force as a result. So, you know, you're not going to be able to work out the exact number, but if you're getting forces here that are more than the applied, just have a bit of a think about whether that makes sense and what sort of a geometry we need to make that make sense. In this case, 18 12 makes sense. Yeah, it's longer than this short.
Put the bolt table up.
Yeah, when you're ready. Oh yeah, we're at that up. Alright, it looks like most people are starting to wrap up. So for A, what do we get for von Mises?
18, 823,
5 pascals on AT, which gave us an AT of what? 94 and change, 94 point something. Good millimeters, and that gave us a bolt of what? 14 by 2. So remember that for A? Easy enough. Alright, B. Von Mises of what?
207, 20.1 on AT.
1 on AT pascals. So that extra 5,000 hasn't really changed our von Mises right here. AT equals, based on proof load, 103.6 millimeters. So again, not a big change. Bolt, same bolt. So 14 by 2. Easy enough? Alright, any questions on that? No? Good. We are going to get more complicated quite quickly. So by the time we add proof loads, things get more complicated, and by the time we add fatigue, things get more complicated. So I wanted you guys to have a really strong foundation in this before we go that way. We'll probably do one of these questions in the tube as well, a little bit more complicated with some portion of things, so you can have another go. When you guys are out and about on the weekend looking for weld groups, why don't you take some pictures of bolt groups too? Because a really good way to study is to do this exact analysis for a bolt group. So for example, if you have, say, a toe ball and a toe bar on a car, you're going to have probably RHS welded to some parts that actually hold it in place, and then that will be bolted to the chassis. So not only do you have welds that you could analyse on that, you have bolts you could analyse on that. Take a photo and a couple of measurements, simplify it a bit, and do this analysis. You can probably find 2 or 3 different bolt groups in your everyday life that will give you more understanding of the fundamentals of this than any textbook problem I can ever give you. So be on the lookout. This subject is great because it's just about everything we can do. We can find real things that we can analyse and actually have a go at. So that's your homework question for the weekend.
So when you've got shear forces like that, is there like stress concentration factors you have to go?
When we do fatigue, yeah, we'll have the same thing as well. It's a stress concentration factor for different threads, and there's different ways to cut threads as well, so you have different stress concentrations as a result of that. But as with everything, stress concentration is important for fatigue, and theoretically not an issue with static loading because you get, that, localized yield that doesn't affect the static loading. Cool. Alright, sweet. Enjoy the rest of the week, guys. See you on Monday.